or beacon-based, you have the same problem, right? Someone can replay the beacons that he picked up at one location to another location. So a device that's located here will hear these 3 beacons and will believe that it is in this red triangle over there. So it's very easy, right? It's a simple replay attack. Here as well, in time of arrival based localization, you can do exactly the same as was done with GPS. With time difference of arrival systems, you can cheat using either directional antennas or any other way. Obviously, for different attacks, you need different levels of sophistication in terms of the equipment that you have, but they are fairly possible. Especially, for example, in ultrasonic based systems, they are fairly vulnerable to many attacks. So why isn't it enough just to say, well, let's encrypt it all, let's hide it all, let's sign our signals, let's sign our messages. So we just sign, okay, I'm the beacon coming from this base station and here's my signature, right? The node that's receiving this can verify that the signature is correct, right? So that should be fine. That should be enough. Well, this is clearly not enough, right? Because all these traditional security primitives don't help here, because the attacker didn't really try to modify this message. He didn't try to modify the content of the message. He didn't try to modify what is written in the message sent by the base station. It simply modifies some properties that you measure, the properties of the signal that you measure in order to obtain your location. So it's violating another type of integrity, the integrity of the time of signal arrival, the integrity of the signal characteristics, and it can also introduce or remove signals from the channel. So we are dealing with a completely different adversary than what we were used to in traditional security, where we talk about the content of messages, where we talk about the content of digital data that is being communicated. So we need something else. So I'll present a system which we recently published this year at Mobicom. It's called SecNav, and it's secure localization or secure navigation, secure broadcast navigation system. So what was the goal of this secure navigation system? Well, we wanted to compute the correct location of a trusted device in the presence of an attacker. So we have a device, B. We have some base stations that we can set up on a campus. And we want to make sure that B cannot be cheated on his location by an external attacker. That's what we want to do. So we want to prevent all these attacks that I talked about earlier. So what are our assumptions? Well, our assumptions are the following, right? We assume that we have an infrastructure of base stations which can be transmitting on different channels. So they transmit on different radio channels using different bands that are covering a certain area, like a university campus, a Purdue University campus. We have a node, the user, that is aware that it is in the campus but doesn't know where it is in the campus. So he knows that he is on campus, but he doesn't know where on campus. And we assume that the attacker can deploy as many stations as he wishes. He can replay, delay, jam, whatever he wants, right? So he can deploy a number of rogue stations wherever he wants. And we want to prevent the attacks that I mentioned. So this requirement here is crucial for this scheme. I'll remove this requirement in some other schemes, but the user has to be aware of its presence in the coverage area, and you'll see why. So he has to know at least that he's on campus. So how does this work? Well, the way that this works is that we are going to send simple, non-encrypted, non-signed beacons from the base stations to the node. So these base stations are going to send beacons which will contain, for example, if you want to have this beacon-based localization, will contain simply, I'm station number 1, and this is the time at which I send my beacon. So just a plain timestamp on a given frequency, right, on a given channel, and we just send that. Please notice that B doesn't share any keys with the base station. It doesn't know the public keys of the base station. He only knows that there is a legitimate infrastructure on site, and it is going to transmit on these channels. That's a pretty simple assumption, right? So, since the beacons are not signed or encrypted, what do we do in order to prevent that these beacons are now overwritten or simply blocked and replaced by fake beacons? What do we do? Well, this is what we do. We call it integrity coding, and it's a pretty interesting scheme which does the following. So you take a beacon, you take this message which will be sent by the base station, and this is a string of ones and zeros, right? It's a message that you generate. What you do is you expand this message using, for example, Manchester coding, such that each one will be converted into 1, 0, and each 0 will be converted into 0, 1. That's very simple. For any message, you will obtain a corresponding message, which now has a very interesting property for us. And that is that it contains exactly the same number of ones and zeros. So, for whatever you put here, you get a message that contains an equal number of ones and zeros. So the Hamming weight, half of the length. And then what you do is you take this message, and then so this is what is done by the base station, you generate a random signal within your frequency band, which is transmitted when 1 is supposed to be transmitted. So it's just the presence of a random signal on the channel. This is what the base station does. It simply takes a 1 and simply transmits something random on the channel. Well, when it wants to transmit a 0, it doesn't transmit. It just says, well, I keep quiet. And the base station keeps on transmitting this all the time. So when the infrastructure is on, the base station just simply transmits this all the time. So this is a kind of unidirectional coding that we do here. So we do some Manchester coding with on-off keying, and we generate these random signals. So now, when we have a receiver, so when we have a receiver receiving this signal, what happens now? Well, we take a very simple threshold-based scheme, right? The receiver sees some signals on the channel. If there is a signal on the channel, it converts it interprets this as a 1. If there is no signal below a certain threshold, it simply says, well, this is a 0. And just keep in mind that here we are not measuring signals to noise ratios or whatever. We just measure the pure energy of the signal on the channel. So what you receive in your antenna, you just register, okay, within this frequency band, I received a certain level of energy, right? And then after you decode this from a signal to the message, what the receiver simply has to check is, does this message contain the same number of ones and zeros? If it contains the same number of ones and zeros, it's a legitimate message. It hasn't been overridden. It hasn't been modified by the attacker in any way. This is the channel. You keep it always busy with such signals, right? Why is this the case? Well, this is why. Because if a base station is sending this on the channel, right? This is a message containing the same number of ones and zeros. If the attacker inserts a signal where a 0 should appear, then the number of ones and zeros will be changed in this message. So at the end, the receiver will notice that now there are more ones than zeros, meaning that the integrity of this message was modified. Doesn't hold, essentially. But if the attacker tries to cancel out this 1 into a 0, he will run into a lot of trouble. I mean, canceling out a random signal on a channel is a non-trivial task. So if you randomize this sufficiently within your band that you can afford, either by changing the phase or by whatever you might think of, you have a pretty good. I mean, the attacker has a pretty difficult job in order to cancel out this signal. So now this job of canceling out the signal. So if you just look, so we call it an anti-blocking property of the wireless channel.